Welcome to Group Theory Lecture 22. So in this lecture we are going to discuss the Second Sylow Theorem. So in the past two lectures we have seen uh, First Sylow Theorem. We have seen two proofs. One was a stronger version of First Sylow Theorem, in which we show that uh, if p power alpha divides order of G, then G has a subgroup of order p power alpha for all alpha. And in that proof we have seen using combinatorial argument, and then in the next video we have seen another proof using class equation. So that was first Sylow theorem. Then we had seen double coset, the concept of double coset, and now this next topic is second Sylow theorem. So the statement is, let G be a group G be a finite group and P be a prime such that P power m divides order of G, but P power m plus 1 does not divide order of G for some integer m. Then by first Sylow theorem we know that it has a subgroup of order p power m, highest prime power. It has subgroup of order p power m, which is called p-Sylow subgroup. But what this theorem says is that any two p-Sylow subgroups are conjugate. So then any two subgroups of order p power m are conjugate. That is, any two p-Sylow subgroups are conjugate. Proof is easy using the concept of double cosets. So we say that let A and B be two p-Sylow subgroups. Existence is guaranteed by Sylow's first theorem. So let A and B be two p-Sylow subgroups of G. Since p power m divides order of G and p power m plus 1 does not divide order of G, we have because they are p-Sylow subgroups. So what are order of A and B? Order of A is p power m and order of B is okay. So let me change this m to n. So as per the notes I'll be consistent. So in the notes I've taken n. Yes, so let it be n. Otherwise I have to change in the notes again. So let us say okay. So highest pi power is p power n. So this is so A and B has order p power n, right? So this we know. What we have to show? We have to show that A and B are conjugates. So we want to show that A and B are conjugate. We have to show that is we have to show that there exists some x in G such that, or there exists some G in G such that some element G in G such that A equals to GB G inverse, or we can say that B equals to GB GA G inverse. So this is just like elements. These two subgroups are called conjugate if there exists such element in G such that A equals to GB G inverse. So this is what we want to show. So now as soon as we have two subgroups, whenever we have two subgroups, double cosets come into picture. So we know double coset is what? So we define an equivalence relation. X is equivalence to y if y equals to axb for some a in A and for some b in B. So as soon as we have two subgroups, we can define this equivalence relation, and the equivalence class for x is nothing but it is axb. So this is double coset, right? So equivalence class means that partitions G into all this coset. So partition G. So now decompose G into double cosets of A and B. Decompose G into double cosets of A and B. So then we can write G as disjoint union of all this, right? Disjoint union. Once classes are there, then the union is G, and the intersection is empty intersection. Either two classes are same or they are disjoint. So the union is disjoint. So then G can be written as disjoint union of AX of the classes, equivalence classes, AXB. So that is we can write G equals to, this is union is disjoint AXB. Therefore we can write what is order of G. Order of G, we can write sum of order of AXB, right? Okay. So where the sum is over all those classes exactly 1x. Okay. So okay, now we know this. Last time we have seen what is the order of this double coset. So what is order of x? So we know that order of AXB, this is we have seen in the last class. This is order of A, order of B upon order of A intersection x, B, x inverse, something like this. Now you see what is the relation here. We want to show that they are conjugate, and here we are coming x, B, x inverse. So to show that A and B are conjugate, we have to find some G. We have to show that there exists. So what happens if we go by the method of contradiction? So on the contrary, suppose this is not true. What is the negation of this? એક માટે થવું જોઈએ, એક G એવો મળવો જોઈએ such that A equals to GB G inverse. જો આ સાચું ના હોય, if this is not true, that means there exists no such G. આવો એકેય G નહીં મળે. એનો મતલબ કે દરેક x લેસ, for every x in G, A is not equals to, for every x in G, the negation of this is, for every x in G, A is not equals to x, B, x inverse. Right? So this is what we use. So suppose A and B are not conjugate. So if A is not equals to x, B, x inverse for every x, suppose our way for every x in G, then so this is what H intersection K. We know that it is subgroup of H. We know it is subgroup of K. And if A is not equals to this, then what will be order of then this is a subgroup, then actually then this is A intersection x, B, x inverse. If they are not equal, then this is a subgroup of A. In fact it will be a proper subgroup of A, right? So A, let me add one page here. Yes. So then order of A intersection x, B, x inverse divides order of A, and therefore order of A intersection x, B, x inverse equals to, let us say order of A is what? P power m, P power n. Yes, A and B are p-Sylow subgroups, so order is P power n. So it is divisor of P power n, that means it is of some power of prime. So it is P power, let us say m, where m is strictly less than n. Why is m strictly less than n? So if m equals to n, that means what? If the order is p power n, that means these two are equal. This is equal, but this is a subgroup. So if these are equal, that means and this has p power n elements, b has p power n elements, so this also has p power n elements, this also has p power n elements. So both have p power n elements, and so they must be equal, but we assume that they are not equal, right? So if the order is equal, so either it is equals to a. If it is equals to a, order is p power n, where m is equals to n. But if it is equals to a, that means a is equals to xb x inverse for some x, right? So it is not possible for all x. We have assumed that suppose this is not equal, because both have same number of elements, p power n and p power n, and the intersection is equals to a. So a થઈ જાય એનો મતલબ કે આના બધા એલિમેન્ટ્સ આમાં હોય, but then all the elements are, how many elements are there? p power n. આમાં p power n, એનો મતલબ કે they must be same. So they are not same for any x, and therefore this order is strictly less than m. So then what is order of this order is strictly less than n? Then what is order of axb? Thus order of axb, which is equals to order of a, order of b upon order of a intersection xb x inverse, which is order of a is p power n, order of b is p power n, and this is p power m. So where m is strictly less than n, so this implies n minus m is greater than 0, or we can write n minus m is greater than or equals to 1, because they are integers. So this will be p power n, and I can write this p power n minus m. So we have p power n minus m. But what is n minus m? This is greater than or equals to 1. So how much prime power divides order of axb? P power n to chhe, and this one is greater than or equals to 1. So we can say that p power, therefore we can say that p power n plus 1 divides order of axb. But then p power n plus 1 divides summation order of axb. This is true for all x, right? This is true for all x in G, because we have assumed that they are not equal for all x in G. ધારો કે conjugate નથી, for all x in G they are not equal, a is not equals to xb x inverse. Then this is true, then therefore this sum also divides. But then this implies p power n plus 1 divides, what is the sum? We have partitioned G into this cosets, so the sum is order of G. So that means p power n plus 1 divides order of G, which is a contradiction. Why? Because which is a contradiction, since we have assumed that to our assumption p-Sylow subgroup no order કેટલો? p power n. So એનાથી વધારે તો order divide ના કરી શકે ને. Since this is contradiction to our assumption that p power n divides order of G, but p power n plus 1 does not divide order of G, right? So this is contradiction in the statement we have given this. P power n plus 1 will not divide order of G. So p-Sylow subgroup has order p power n. It cannot be more than that, otherwise that is not p-Sylow subgroup. So yeah, okay. So what we do is as soon as we have what we want to show, they are conjugate. So there is some G such that a equals to bg, b inverse. Then we say that a and b are conjugate. This is what we have to prove. Suppose there is no such G, so that means for all x, a is not equals to a x b x inverse. Okay, then now what a and b are there, we partition G into double cosets. So this union is disjoint. Because it is disjoint union, it is exactly sum. Remember I said if I want to count the number of students of department, because there is no common student, so count the number of students in first class, class 1, and then count the number of students in class 2. So we can write as sum. Otherwise we cannot write this. But because the union is disjoint, so this is so this is disjoint union, and therefore what are the elements? Number of elements in G, that is order of axb. But we know what is order of axb, order of a up into order of b upon this. So if they are not equal, then this is a subgroup. In fact, it will be a proper subgroup. It cannot be A. Why it cannot be A? Because if this is equals to A, the number of elements here is p power n, which is same as A. And if it is, and number of elements here is p power n, here also p power n. So intersection also has p power n elements. That means these two are same. But these two are not same for all x. Therefore, it is a proper subgroup. And once it is proper subgroup, the order divides order of A. So it is of some prime power. Order of A is nothing but p power n. So some prime power m, but where m is strictly less than n. Okay, so it is because it is proper subgroup. Okay, then order of AXB will be p power n upon p power m. So this p power n as it is, and then p power n minus m is greater than equals to 1. So there are n powers already there, and this is at least 1 power. So I can say that p power n plus 1 divides order of AXB, and this is true for all x because this is true for all x, we assume. Right? So that means p power n plus 1 divides the sum, and hence p power n plus 1 divides order of order of g. Right? So that which is contradiction, because highest prime power dividing order of g we assume to be n. So p power n divides order of g, but p power n plus 1 does not divide order of g, and therefore it is contradiction. Therefore, hence we can say that a equals to x be x inverse for some x in g. Earlier we have assumed, આપણે એવું assume કર્યું હતું કે it is not equal for any x, but now it is for some x in g, that is a and b are conjugates. Right? So as a corollary, we have a very important result, that a unique p-Sylow subgroup is normal. A unique p-Sylow subgroup is normal. So let G be a group such that p power n divides order of G, but p power n plus 1 does not divide order of G. And let P be a p-Sylow subgroup. P be a p-Sylow subgroup of G. What is p-Sylow subgroup? Highest prime power. So P be a p-Sylow subgroup of G. Then what is order of P? Then we know order of P is p power n. Highest prime is n plus 1 will not divide. So highest is n. So order of this. Now for any x in G, for any x in G, we know this x p x inverse. What is x p x inverse? This is also, if p is a subgroup, x p x inverse. In last time we have done this exercise in the last lecture. So if h is subgroup, x h x inverse, or a h a inverse is also a subgroup. So if p here is a p-Sylow subgroup, then for any x, x p x inverse is a subgroup of G. And not only that, this is isomorphic to P. So if it is isomorphic to P, order is also same. This is also what we have seen last time. So order of xp x inverse is same as order of P, which is p power n, which is also highest prime power. So that means this is also p-Sylow subgroup for every x. So that is thus for every x in G, x p x inverse is a p-Sylow subgroup. X p x inverse is a p-Sylow subgroup of G, because this also has the highest prime power. Order is same, both is p power n. But what we are given? We are given that G has a unique p-Sylow subgroup. That means for every x, this cannot be different from P. Unique છે ને, P થી બીજું તો ના મળવું જોઈએ. There is only one. So since P is unique p-Sylow subgroup, since G has unique p-Sylow subgroup, unique p-Sylow subgroup, we have, so what we have, this cannot be distinct. Both are p-Sylow subgroup, both have the same order, but then it cannot be distinct. So what we have xp, x inverse equals to p for all x in G, hence p is normal. This is definition of normal. xp, x inverse is p for all x in G, hence p is normal. As an example, we can consider S3. In S3, the p-Sylow subgroup, the 3-Sylow subgroup, which is unique. The 3-Sylow subgroup generated by psi, which is E psi square, is it's a unique. There is only one subgroup of order 3 in S3. It is unique. Right? 3-Sylow subgroup. What is S3? Order of S3 is 6. 2 into 3. This is 6. So 3-Sylow subgroup has order 3 power 1. That is 3. So this is unique and આના સિવાય બીજું નથી મળતું. Unique 3-Sylow subgroup. Right? So highest power of 3 dividing this is 1. So 3 only divides. So this is unique, and hence it is normal. So this way also we can say that this is normal. Subgroup generated by psi is normal, hence it is normal. Right, now the question is, what about the converse of above corollary? If p-Sylow subgroup is normal, can we say that it is unique? So that is I leave for you to think. So what about the converse of the above corollary? Right, what about the converse of above corollary? That is, if so unique p-Sylow subgroup હોય તો normal હોય. Suppose a p-Sylow subgroup is normal, is it unique? That is, if a p-Sylow subgroup of G is normal, suppose p-Sylow subgroup is normal, then is it unique? That is the question. Right, so think about this. So now we count the number of p-Sylow subgroups of G. So now we exactly count the number of, so now we determine the number of p-Sylow subgroups of G. So for this, we define something what is called normalizer. Right? So let us define. Let H be a subgroup of G. So normalizer of element we know, Na. Now this is normalizer of subgroup. So then the normalizer of H is the set NH such that all x in G. What was NA? XA equals to AX. So this is XH equals to HX. So for which the left and right cosets are same. All those x, that is called normalizer of the subgroup H. Right? Normalizer of subgroup H. So that is this set. If H is normal, then normalizer is entire XH equals to HX. Left coset is same as right coset. Normal na case ma. તો પછી NH શું થઈ જશે? આખું G થઈ જશે જો normal હોય તો. If it is not normal, then it may be a proper subset. proper subgroup. Okay, so normalizer we have defined, and now let us state the number of p-Sylow subgroups in G. So this lemma gives the exact number of p-Sylow subgroups in G. So let lemma, the number of p-Sylow subgroups, the number of p-Sylow subgroups of subgroups in G is equal to exactly this, order of G upon order of NP. What is NP? It is normalizer of P. But what is P? So P is where P is. So first we have to find one p-Sylow subgroup where P is any. P is any p-Sylow subgroup of G. Yes, so in particular we can say that this is a subgroup, right? Just normalizer of A is a subgroup, so normalizer of H is also a subgroup. You can try that exercise. So if order of subgroup divides order of group, so this is order of G upon order of NP, that is a divisor of order of G. So in particular, the number of p-Sylow subgroups of G is a divisor of order of G. It is also a divisor of order of G. So what this result says, it gives the exact number of p-Sylow subgroups in G, and which is very important. But unfortunately, we are not able to apply this in practical examples, because what is the reason? I'll tell you. So number of p-Sylow subgroups in G, this is small p. P-Sylow subgroups in G is order of G upon order of NP, where what is P? This is capital P. P is any p-Sylow subgroup. So if we find one p-Sylow subgroup, then we can find NP, and then order of G upon order of NP gives the exact number of p-Sylow subgroups. So for which we need to find one p-Sylow subgroup for that, or at least we need to find order of NP. So that is why it is, for examples, it is not much useful. We will be using Sylow's third theorem in the example in applications. But anyway, this gives the exact number. So in particular, it is divisor of order of G. Right. So let us see the proof. Proof is not difficult. So what we have to prove is number of p-Sylow subgroups is this. So let us consider the collection. Let P be the collection, script P. Let P be the collection of all p-Sylow subgroups. Let P be the collection of all p-Sylow subgroups of G, and suppose one such element we take, P in P. So what is P? P is a p-Sylow subgroup. So that is, this means P is because this is collection of all p-Sylow subgroups, and P belongs to P. So that means P is a p-Sylow subgroup of G. Right. So since we have seen any two p-Sylow subgroups are conjugate, so elements of P can be written as P ni andar kya elements hoy, all are p-Sylow subgroups. So we have P1, P is there, then some sub P1, P2 and all, but all this, they are conjugates to each other. Any two p-Sylow subgroups, they are conjugate. So P1 I can write as some x P x inverse. P2 is also conjugate of P. So P2 I can write as x, so y P y inverse for some y. So any p-Sylow subgroup is a conjugate of P, because any two p-Sylow subgroups are conjugate. So therefore any p-Sylow subgroup I can write as some x P x inverse. So since two p-Sylow subgroups are conjugate, since by this is second Sylow theorem, by second Sylow theorem, any two p-Sylow subgroups are conjugate. Elements of P can be written as, so every element of P can be written as of this collection. It's a p-Sylow subgroup. So એને કેમ લખાય? We know one. So any element is just a conjugate of this. Every element of P can be written as x p x inverse for some x in G. Right? This is the notation of all the elements of P. Yes, and now we want to show that this is collection of all p-Sylow subgroups. We want to show that total number of p-Sylow subgroups is this. So we want to show that cardinality of this, right? We want to show that the cardinality of this is same as order of G upon order of NP. So what is cardinality? How do we show that cardinality of two sets? Oh, what is this? Order of G upon order of NP. This is nothing but index of NP in G. Right? What is order of G upon order of H? This is nothing but index of H in G. So what is order of G upon order of NP? Index of normalizer of P in G, index of NP in G, and that is same as this. So index ni definition શું છે? So that is nothing but order of G quotient NP, order of G quotient NP. So we define a map. So let NP denote the normalizer of subgroup P. Now define. Let us define phi from P to G quotient NP. Okay, G quotient NP. So our quotient क्या लेवाय? It should be a normal subgroup, right? So let me write an exercise here when I have defined. Exercise. Show that NH is a normal subgroup of G. Yeah, so define this map. So once we define and we show that it is on 1 1 and onto 1 1 correspondence, then we are done. So define from script P, which is collection of all p-Sylow subgroups, to G quotient NP by, how do we define? So I need one element here. I know one element. एक तो है p-Sylow subgroup. I know P is p-Sylow subgroup, right? So one element I know, but how to define in general? આના બધા એલિમેન્ટ્સ કેવા હોય? તો કે that is what we have written. Since every two p-Sylow subgroups are conjugate, every p-Sylow subgroup can be written as conjugate of P. That means xp x inverse for some x. તો આના general element કેવા હશે? If I want to write P, then it is EP E inverse. But any other element which can be written as xp x inverse. And once I have this xp x inverse, I need a coset of NP. So that will be, coset of NP will be, let us take NPX. So coset of NP. So once we have x, we define here NPX. Then we show that this is well defined 1 1 and on 2. So to prove this result, we show that phi is a well defined bijection. So it's a well-defined function and it is a bijection, that is, it's a 1 1 correspondence. The number of elements here is same as number of elements here. So what is this? Collection of all p-Sylow subgroups. That means total number of p-Sylow subgroup is same as total number of elements here. So what is order of G quotient NP? So that is all distinct left or right cosets of NP in G, which is index of NP in G. So order of G upon order of NP. This is what we have to prove here. We are done. So just we have to show that this function is well defined 1 1 and on 2. So let us take well definedness. So first we take xp x inverse equals to, let us say, yp y inverse. So this implies I can write, I multiply by x inverse on the left. So we have p x inverse equals to x inverse y p y inverse. Now multiply by y on the right. So we have p x inverse y equals to x inverse y p. So what did we get? So that means if I call this my element z, if I call this z, so what do I have? I have something like this, pz equals to zp. pz equals to zp, તો શું થાય? xh equals to hx. Then we can say that x belongs to the normalizer of h, by definition of normalizer. ઓલામાં n એવું કરતા ને x a equals to ax, then x belongs to na. So here pz, this is my z, pz equals to zp. So I can say that that element belongs to the normalizer. So this implies x inverse y belongs to np. If x inverse y belongs to np, that means x inverse y or x inverse, so that means the right cosets are also same. So npx equals to npy. So right cosets are same, but what actually we are getting here, if we write like this, so we have x inverse y np equals to np. If the element belongs to this, if a belongs to h, then ah equals to h. So if so this is h. So x inverse y belongs to np, then x inverse y np equals to np. This is what we have. Then we multiply by x. So what we have, actually we have this y np equals to x np. So we are getting left cosets here. The reason is this Herstein notation, we are in the reverse side, so we are getting like this. But anyway, this is normal. So because it is normal, left coset is same as right coset. So we have npx equals to npy. So left, so this is, what is npx? Npx is nothing but phi we have defined, right? Phi of xp x inverse. This is same as phi of yp y inverse. So this way, when we come down this way, it is well definedness, and we can also apply this. So this implies it is 1 1. So thus phi is well defined and 1 1. Yeah, and now on to what we do, we take an element here. Element of this is g quotient np. કેવું હશે? It is a right coset of np in g. So for onto, let g quotient np, we want element in g quotient np. So we have to take let npx belongs to, so let npx belongs to, because this is the way, there is no other yeah. So element is nothing but right coset. So npx belongs to g quotient np for some x in g. This is how cosets are defined, right? So as soon as we have x, we are done. As soon as we have x, we have a p-Sylow subgroup. This is collection of all p-Sylow subgroup. તો આમાંનો એક એલિમેન્ટ મળશે, કેવી રીતે મળશે? એક p-Sylow subgroup જોઈએ. p we know. So as soon as we have x, then xp x inverse is also a p-Sylow subgroup. Because p is a p-Sylow subgroup, so this is also p-Sylow subgroup. Why? Because order of xp x inverse is same as order of p. So બંનેનો highest prime power વાળો જ order હશે. P is a p-Sylow subgroup, then xp x inverse is also p-Sylow subgroup of g, right? And so that is xp x inverse. xp x inverse શેમાં મળશે? This is in the collection of p, collection of all p-Sylow subgroups, and apply phi on xp x inverse. xp x inverse, this is nothing but npx. This is where we started. So hence phi is onto. So hence phi from phi is a 1-1 correspondence between the collection P of all p-Sylow subgroups of G and G quotient NP, right? So that is a set of the group of all distinct right cosets or left cosets of NP in G, and because it is 1-1 correspondence, they have the same number of elements. So hence, then the cardinality of this, what is this? Collection of all p-Sylow subgroups. So hence the number of p-Sylow subgroups, hence the number of p-Sylow subgroups of G is equals to order of G is cardinality of this. So actually it is nothing but order of G quotient NP, that is order of G upon order of NP. And because NP is a subgroup by the order of subgroup divides order of group, so this is a factor. So like this, order of this is 6. So 2 divides 6. So 2 upon 6 upon 2, that is 3. That is also a divisor. 6 upon 3, that is 2. That is also a divisor. So this is in particular, this is a divisor. In particular, the number of p-Sylow subgroups in G is a divisor of order of G. Right, so in the next class we'll see third Sylow's theorem. So okay, I stop here.